Hi everyone, I'm Shreya. I study computer science, and my project is visualization and analysis for a home-based system for physical therapy. My advisor is Dr. Margaret Betka, who's also of the computer science department. So I'd like to start by giving you an overview of how the system that we're trying to build actually works. So this is how the workflow would go. So a physical therapy patient would come into the clinic and have their exercise recorded, but under the supervision of their physical therapist. And this would be the gold standard or the patient's personal best of that exercise. Then the patient will go home and record and try and practice the exercise with the comparison of their reference exercise and the reference exercise as a model. And then we would provide analysis and feedback that shows accuracy, speed, and frequency of exercise practice at home, which is viewable by both patients and clinicians and allows for communication between the patient and physician. So why do we need this? A lot of the times, physical therapy patients it's very strenuous for them to travel back and forth from the clinic. So having a more accessible option at home to do physical therapy exercise at home is very important. Also, most physical therapy patients should be practicing exercises at home, as far as I understand. And a lot of the time when you practice exercises at home, you may do them incorrectly, and this could hinder your progress, if not take you backwards on the road to recovery. So the team that worked on this was the Image and Video Computing Group, which is a computer vision lab headed by my advisor, Dr. Margaret Betka, and as well as the Software Application and Innovation Lab, which is a team of software engineers that are working on packaging this application so that patients and clinicians can eventually use it easily. We're also working with Dr. Teresa Ellis and Sargent College and getting feedback from actual physical therapy patients and clinicians, which has been one of the most rewarding parts of this experience. I've been working as a part of this team since January 2017. So the technology that we use for this app is the Microsoft Kinect as the hardware input device. This is important here because we can actually capture data in 3D and therefore map orientation and posture, which ends up being very important for physical therapy analysis. We also are using the Microsoft Kinect because there's a wide range of software development kits that are around it, so we could take our pick of how we wanted to build our app. And in this case, we're using a software development kit that interacts with JavaScript. We're also now working on transitioning the application into a Node.js application framework so that it's easier to package and deliver to outside users. And we also use Python for certain scripts. Quick note about the Microsoft Kinect. Right now, that's a replaceable part of our project because, as I mentioned, the important part about it is that it captures 3D data. And as the technology in that improves, it's turning out that we don't need it anymore, as even our smartphones can capture 3D images. So hopefully, eventually, maybe in a year or two, we can just use our iPhones for something like this. So I worked on both the software development as well as the computer vision research of this project. So I'll start by talking about what I did with the user interface and software development. One of the things that we did was make sure that our application adhered to accessibility guidelines. So here's an example of what the prototype looked like about a year ago, whereas the improved colors on the right side of the screen. This is basically making sure that visually impaired users as well as other disabled users would be able to use our app with the same ease that able-bodied people would be able to. Another thing that we ended up doing was showing different versions of our application to our patients and clinicians and ask them what exactly they preferred. So for one of the things, I'll show you guys a quick example of that. And that was, if you remember, we recorded the reference exercise that the physical therapy clinician had deemed as the ideal or reference. And with that, that would act as a guide when the patient was doing the exercise at home. So we weren't sure what the best way to represent both of those skeletons would be. And one of the ideas we had was having it superimposed like this. So these are both me. But the light blue, the light blue is my reference, which is like my supposedly like perfect exercise. And the one in the blue is what I would do if I was at home and trying to follow along with it. So this would act as a guide. And turns out patients did not like this at all. It seemed like very distracting and that they were confused. They didn't know which one was them, which one was the actual reference exercise. So we ended up showing them this one also, where the green one is actually the reference exercise and the blue one is me following along with my reference. so I know exactly what I'm supposed to be doing. So beyond that, for the software development part of it, I have been writing APIs, moving code over to the new system, and doing a lot of testing to make sure that the app is robust for when we actually release it for patients and clinicians for eventual use. Now, for the computer vision aspect of it, really quickly, computer vision is a branch of artificial intelligence that deals with image processing and analysis. The reason that we use this here is a software development kit that captures data from the Kinect, actually captures them as body frames. So they're basically a bunch of images, and we look at the points in each image, and that's how we process data in our application, which is why these techniques are especially useful to be used here. So one of them that we used was dynamic time warping. Dynamic time warping is a technique where we can identify with two sequences of data, find paths between them so that we find the closest path between each point. So the way that works here is that we can identify acceleration and deceleration in two sequences. So if I did a squat in the clinic and it was at a certain speed, and then I went home and I did the squat correctly, but it was extremely quick, I could still identify that all the points were hit and that it was actually a correct squat. The other aspect that we looked at was calculating speed. So for this one, we tried a couple different methods. One of them was looking at acceleration in real time, but Dr. Ellis from Sargent College told us that this actually isn't the best way to give feedback to patients. Patients would rather prefer to have feedback given to them post-exercise or post a complete set. So we ended up calculating speed distance over time, which ends up being the total change in points from each body frame over the total time taken for the exercise. The problem we ran into here was that patients often, and all of us probably, when we do our daily exercises, when you do squats or any kind of exercise, between repetitions, we tend to pause a lot. And this was messing up the speed of the data because it would increase the time and it would look like they were taking a lot longer to do the exercise than they actually did when they did it in the clinic. So to address this, we're using a technique called movement arrest period ratio, where we first take the average speed of the entire data set, as I mentioned, distance over time, and then we split up the sequence into smaller segments, take the speed of each small segment, and if the speed of it is less than 50%, we discard that, and then we retake the speed of the entire sequence. And this ended up showing us that when I did the squats and I took breaks, longer breaks between each repetition, this was giving closer speed to each to the original reference data. And then the other computer vision challenge that we worked on is counting repetitions. So obviously, post-exercise, counting repetitions is a little more easy because we can look at the local maxima and minima of the data of the salient axis, which ends up being the axis where you have the most movement. But in real time, this is more challenging, mostly because there is a lot of error when it comes to patient data. If you were doing a perfect squat, again, it would be easy, but because patients will move, and especially since they're doing physical therapy, we don't really know what other challenges we might run into. We are using a system where we have a threshold. The maximum and minimum dip is based on our reference exercise, and then we have a margin of error, and as long as patients hit both thresholds, it will count as a repetition. We've also looked into other techniques like convolutional neural networks for counting repetitions in real time. The challenge we have here right now is we don't have a lot of patient data in the format that we want, because we want it through the Kinect software development kit as well. So that is probably something to do in the future. This is an example of the dynamic time warping. This is the original data on the top, and the bottom is the aligned data. So future work includes, I'll be on this project until the end of June. Future work includes experiments with patients. Like I said, we need to gather more data, more explorations on these problems that will come up as we do more experiments with patients and see more patient data. And eventually, we plan on releasing this as an app for patients and clinicians to use. Thank you. I can take any questions.
What's the time scale for the release of the app?
Oh, I'm not sure. Probably, I'm guessing around October, November of this year. It would be a first version. Yeah. Okay, thanks.